Alright, I should probably unfreeze my screen. Anyone real confident with their drawing and think you made it look nice that we could just show it up here to the class and then we can talk about it and explain it together? Braylon, you want to bring me yours while I load up the dot camera? Alright, so Mr. Vilo is going to explain his drawing. Or somebody else can explain it, I guess. Alright, so MNPQ. Now, as soon as the camera loads up. What do you mean the apostrophe? Oh, the, like, prime? Yes, but we don't call it negative. We just say M prime, N prime, P prime. So, great question from Braylon of did he make his notations correct? So, check out Braylon's graph. Please check that you oriented your XYs correctly. M, and I think these are just dashes that he put here, but don't. So that makes it look like negative. So if I were to make feedback on Braylon's graph, I would say don't make those dashes. They make it look confusing. But so there's his M. His M prime is twice as far away from the origin. There's his N. N prime is twice as far from the origin. P, P prime, Q, Q prime, perfect. Right? Any issues with this graph? So then the question asks us, what can we say about angle M versus M prime? Braylon, what do you think? Talk to the class. You're teaching. You're in charge. Can anyone talk about your conjecture about M and M prime?
Well, you can't really make a good conjecture if you don't draw the graph right.
Well, okay, but if you drew the graph right.
We used to think that angle M looks, angle M is the same angle in both M and M prime.
Seriously, can no one tell me why we aren't using three-point notation?
Because it's unneeded, because they're all the same angle.
Not they're all the same angle, George.
Is everything a right angle?
We don't know that. Even if it's a right angle, we could still use three-point notation. Are there multiple angles at M?
Yes.
Ignore the y-axis. It's an axis, right? There's only one angle M. It's the inside angle of the shape. So guys, three-point notation is necessary when there's multiple angles with the same vertex. At vertex M, there's just angle M on the inside of the shape because we don't talk about the outside angle. We talk about the inside angles. So, and it looks like it's 90 degrees. We're not sure. But so we have our angle M, and that's why we don't need three-point notation. We could three-point notation, though, and it'd be QMN or NMQ. Remember, the vertex goes in the middle. Who's got a conjecture about M compared to M prime? M compared to M prime. Ooh, yeah. Oh, well, you were right, though. They both sit on the y-axis, right? They're like directly above each other. What about the x-axis? Yeah, so the x values for both of them are 0. What about the size of the angles? You know, you can test a right angle. Use something that's a perfect square. Use the corner of your ruler. See if you think angle M is a right angle. Careful with your computer screen. Don't poke it. Like, seriously, you can actually poke it. It should be perpendicular, though. The two sides of it, even if it rounds the corner, it should be perpendicular. No. I hear the questioning, or are you sure you did it right? That's what your shape should look like. That's what your shape should look like. So, guys, when I look at M and M prime, if I slide this rectangle down onto here, like if you use your ruler or whatever else and you try to compare them, don't these look like they're the same size? Like when we talk about how big an angle is. Now, we talked about triangle angle sum the other day, but then somebody brought up a quadrilateral sum rule on Tuesday. And I don't know that it's one that we've talked about, but how many degrees does a quadrilateral always have in it?
360.
360, right? So this quadrilateral has to have 360 degrees, and this quadrilateral has to have 360 degrees. So now Connor said something as we went into this problem. He said, so wait, I'm doubling it. And I said, well, yes and no. You got to be careful with what you're asking. And this was a problem that I gave you guys on a mastery test. Why would I say that you have to be careful with saying that the prime shape is double the original shape? I mean, my scale factor was 2. But why am I telling you have to be careful? Hint, hint, nudge, nudge. So many of you got it wrong. I'm going to bring the same problem back again. Why can't we straight up say it doubled? What didn't double, I guess, is the better question. Angles look like they stayed the same, right? So angles don't double. What else doesn't double? Guys, the farm, the acres problem. You started with 1 acre, and the farmer extended his fences. Caitlin? The area. What about the area? When I double lengths, what happens to the area when we double the lengths? Absolutely. When we double the length and the width, or you could call them both lengths. Some people just start saying that length and that length. When I double both of them, guys, the area is quadrupled. Remember back to the acre problem. If I triple the length and the width, or dilate by a scale factor of 3, what happens to the area? Not 6, 9, because it's 3 times 3. 3 times the width, 3 times the length makes 9 times the original. Right? Times 3 times 3 makes times 9. Does that make sense? Your face still looks upset about that. You look like you're still processing. So, I want you to do me a favor. On your graph paper, make a triangle. Don't make it super huge because you're going to want to use it, but I would maybe say do it down in quadrant, that lower left quadrant, because you have space. Make a triangle. Whatever triangle you want, I would suggest putting them on vertices, like where the lines cross. Don't make it in an awkward shape. Then dilate it by 3. So, warning, don't make it huge. You're going to dilate it by 3. You know, I'm going to take some liberties here. This is really close to what we call one of our special right triangles. Now, in honest truth, this is not exact, but if we imagine with me, let's say that this angle I have here is 30, this angle I have here is 60, and this angle I made a right angle because that's the easiest type of triangle to draw is a right triangle, right? Especially on a graph. Right triangles are the easiest to draw. Is there anything I could say about my red triangle then as I look at that dilated new shape? Mallory? That this upper angle would be 90. This angle right here would be, sorry, I switched around my 30 and my 60. My apologies. My angle down here would be 30, and my angle up here would be 60. Now these two triangles now have a special relationship, talking about how they're like kind of the same, but not quite the same. Anyone remember what that's called? What shapes are that are like the same shape but different sizes? I can't tell if that's a hand or if you're just like stuck thinking. Yeah.
Congruent?
No, that'd be if they're the same size. So you're on the right track. Same shape, same size is congruent.
Similar?
Similar. Everyone write down similar figures.
I'm pretty sure we wrote down similar stuff earlier in our notes.
We did.
Wait, Mr. Hudson?
Yeah?
You only made yours twice as big, and you said to do 3.
My smartboard's only so big. It doesn't matter what size you dilate it. I just wanted you guys to be able to see the angles stay the same. So, write down similar figures. Same shape. Different size. Now put size in quotations. And the reason we're going to put size in quotations is a big critical note about similar shapes or similar figures. All angles stay the same. And the reason we put size in quotations is, as we just talked about, does the area change the same as the length? No. So if the length's triple, the area is 9-tupled. If the length's double, the area is quadrupled. I'm confused at what's going on. Are you guys going somewhere? Oh, yeah. But don't go until they call you, because the bus might not be here yet. I mean, normally, let me check with the office, but they normally call you guys. So, here's, before orchestra people leave, the big thing you need to know from this lesson. In a triangle,
Good morning. Could we please
you're going to give me
Jacob
30 seconds.
Lindemeyer to the office. Jacob Lindemeyer to
You're
the
going to give me
office,
30
please.
seconds.
Also, we'll need all of our orchestra students
Don't
to
go.
the commons area.
You're
for
giving me
your
30
rehearsal.
seconds.
Orchestra students, please come to the commons for your rehearsal.
I promise, 30 seconds. If I didn't know this right angle, and I didn't know this right angle, but yet I knew that both of these triangles had a 30-degree angle and a 60-degree angle, could I figure out their third angles? So this brings up a new rule that lets us like shortcut two things. This is called angle, triangle, similarity. That's all I need you to know. Write that down later, like in your notes or in your homework or whatever. If two angles are the same in two triangles, well, the third one has to be the same. And then they're the, not same, but they're similar shapes. That's why it's angle, triangle, similarity. Go. Have fun.
All angles stay the same.
All angles stay the same. My line just went kind of through it.
Okay.
So angle, similarity, guys, is a shortcut to being able to prove, oh yeah, this has to be that, this has to be that. Like these have to be related to each other. So if we go back to our textbook. Sorry, I had to do that out of order because orchestra people leaving, so I wasn't going to just spoon feed that to you. So check this out. Try to draw this on your paper really quick. And I'll show you how in my draft paper. You're going to need your straight edge still, which is why I wanted us to use straight edges but not bend them. Snapple, I'm going to need to copy this page and clear it. Check it. I'm going to keep my vertical line. You're going to need a straight edge on that vertical line, but if you on your graph paper can make something, I don't know, like 5 wide, come down, maybe 3, come down, draw it however you want. Let's set these things are straight. I think that'll work, whatever the count on that is. Yeah, so if I put that dot between like 2 and 3. What do we know about this? Really? It's a right angle, right? One's horizontal, one's vertical. We know that. That's one of those mathematical rules that we've now got comfortable with. What do we know about this angle? Right angle. Who can tell me what else we know? Who can tell me what else we know in this diagram? You might need to use 3-point angle notation. I'll give you a minute. We are able to prove these triangles are similar. Take 30 seconds to think about how. Just in your own brain, think about how we can prove these are similar. We only have one angle right now. So that's what we already wrote on our paper. All right, anyone got any ideas? Connor?
ACB is similar to ECD.
Now be careful, do you mean similar? ACB. You said ACB.
Similar to ECD.
ECD. Now you don't mean similar. You mean congruent.
Oh, yeah.
So, because you mean they're the same, right? Similar means same but different size. So we don't, when we talk about angles, guys, we don't talk about angles as similar. They're either the same or not, right? So if they're the same, we use congruent. Please write this. It's an equal sign with a squiggly on top of it. I'm not joking. This is the math symbol for congruent. I'll write it a little bit darker. Equal sign with a squiggly. It's like hieroglyphics, right? It's like we're still using these symbols that we all recognize to mean something else. So why? Why are those two angles no, I hate myself. Those two angles are vertical, so they prove that they're congruent. Is anyone confused on how this is one straight line and this is one straight line? So these angles are opposite to each other and therefore must be vertical, which then we know means congruent. Any questions? No? Okay. So then, once we have angles congruent, what can we say about these triangles? Not that they're congruent, but that they are similar. Now, here, is where it's really dangerous, and this is where people screw it up. So put a little box or something. We're going to write our similarity statement in here. So put a squiggly in the middle that means similar. We don't use an equals under that because it does not mean congruent. It means similar. If I write triangle in the order of A, B, C, what does the order of my other triangle need to be and why? Because order matters, and I've written this on a lot of your papers already, that order matters. Micah?
EDC?
Why?
Because E equals, well, they have the same angle, E and A have the same angle, and they both come first, and then D and B are both right, and then come second.
By the way, your shirt is awesome. Exactly what Micah just said. The related angles have to be in the same places. So angle A relates with angle E, and we know that because we didn't look at either of them. We know they're the same because the other two angles are the same, but A relates to E. We know that. B, our right angle, relates to D, our right angle. Hence, sorry, those guys relating to each other. And then C is C in both of them. C. If you write this in the wrong order, like you write C, D, E, it's wrong. Because triangle ABC is not congruent to triangle CDE, it's congruent to triangle EDC, which is also Electric Dance Carnival.
So it's not shed, but Ed. So it's not Ed, but.
Yeah, it has, if I go ABC, it has to be EDC. If I went CBA, it would have to be CDE, right? Any change in order, I just change the other one. Questions on why order matters? The corresponding angles have to be in the corresponding locations. Yes?
So can you write BAC and then DEC?
Yep, so if I go right angle, acute angle, well, they're both acute, but if I go right angle, unknown angle, vertical angle, so BAC back, I would go right angle, unknown angle, so back would relate to deck, right? BAC, DEC. I can do that. There are many ways to write this. All right, if there are no questions on that one, check out 43, and we're pulling lots of information together. So talk with your partners, read what they said, and actually I'm going to keep it zoomed in this far so that's all you can see. If you have a book, you can read on, but what relationships do we see here? I'm going to freeze the screen for a second too because I don't want you guys to see what I'm doing. Now I froze the screen. The video's still going, so the video can see what I'm doing. I don't mind that. Dr. Smith, I owe so much of my math skills to you, sir. Oh yeah, Dr. Smith and I have telepathy. He can totally hear me. I'm joking. Anyone know why there's something special here we can deal with or do? What angles can we relate to each other? Because Eleanor's like, this is super easy. And I hate that word. But Eleanor thinks it's easy because she's identified something already. Savannah?
I think
You think E and B are similar? Now, you don't have to use 3-point because there's only one angle E and one angle B. Why do you think they're similar?
because the line EE crosses over the top and makes like a smaller triangle. But if you take that away, B
So if we call this 3 and 4, you're saying angle 1 is congruent to angle 4, or sorry, 3. What would we, why though? What justification? Like, what do we call that? What's the mathematical name for where those angles sit with each other? You can't remember. I think you got some friends that can help you out. Well, I don't know. We're all friends here, according to my book. Micah, Braden, what do you guys think? Not supplementary. If we extend the lines out, if we Dr. Smith this thing, I should really just say Smith, like, because a Smith is somebody who works on something, right? So if we Smith this problem, guys, these are our parallel lines with a transversal. Remember Monday? Parallel lines with a transversal. Those posters right over there, parallel lines with a transversal. Angle 1 sits on top and to the right. Angle 3 sits on top and to the right. What do we call that? I'm just going to sit down and be sad. Two things in the same place starts with a C. They are congruent, but why? See me after class for a piece of candy. I wish I could give away money when that happens. Corresponding. I had a choir director who used to give away $1 once for practice. Like, if you had that special knowledge that no one else could figure out, and you're like, oh, I got it, I remember this. Corresponding, guys. Please write this down again, because that's kind of dramatic that we don't know that. These two angles would be corresponding. Do we have another pair of correspondings? Braylon? Yeah, angle 2 and angle 4. Then I have a new word to teach you. Everyone take your own. Flex. Let it go. Flex. Let it go. Flex. Let it go. Oh, by the way, yesterday when we were at that other school, sorry, my brain's a weird place. They started class with a workout. They're going on an 8th grade trip, like we are our 7th grade trip, and they started class, and I got down and did it with them, with 50 where you put your leg up. 1, 2, 3. Yeah. Then they did planks, like high planks and low planks, and they did yoga. It was sweet, Russian twist, right? It's got like 5 different names, but I thought that was really interesting. When you take your muscle and you flex it, is it still your muscle? Yeah, is it still in the same place? Yeah, it doesn't go anywhere. There's a property in math that deals with something being the same but used in 2 different applications. Angle A is used in this triangle. But angle A is also used in this triangle. So we can actually make a statement, and we don't actually need to here, because guys, have we already satisfied angle-angle similarity? Yes. Yeah. One set of congruent angles, another set of congruent angles. We already have angle-angle similarity here. But we can make the statement of angle A being congruent to itself, which seems unnecessary. But guys, in math, if you want to use knowledge, you have to state it. So when you get up into high school math, you can't just use the fact that angle A is equal to angle A unless you write it down. And then you have to have a justification. This, in math, we call the reflexive property. Now, I can't really think of any good memory tricks aside from the fact that when you flex your muscle, it stays in the same place. It is still your muscle, and it doesn't change what it is. It might get bigger and go out further, right? Those lines extend out further, but it's still in the same place. It's still your muscle. It's still angle A. Anytime we relate a side is equal to itself, like a length is equal to itself, or an angle is equal to itself, that's the reflexive property of congruence. Now, we don't actually have to use that here, but if we did use that, we would have only needed one of these sets of corresponding angles, because then we have our angle, right? If I know angle A is equal to itself, and then I know 1 is equal to 3, or E is equal to B, I know my triangles are similar. And we already are told that they're similar, but then we can work it a bunch of different ways. Today got kind of weird because your classmate's leaving. All right, so John is looking at this thing. He says, okay, I get you, right? I'm with you. I understand these triangles are similar now. And I forget the other person's name. Yeah, Eleanor says, you know, John, we can then use this to solve for unknown pieces. He's like, sigh. More work. So she pulls out triangle AED and says, well, the problem is we don't know what AD is. But we do know what DC is. Similar triangles create what we call a similarity ratio. Gravity works. All that really means is if I say, and please write this down, we'll go ahead and say similarity ratio. If I relate small to big, that is equal to any other relation of small to big. So Eleanor says if we know our similarity ratio is allowed to hold true, then I can write this. My small side related to my big side, right? 3 is my small side, but my big side is the whole thing, 3 plus 5. And then I can relate that to small side compared to big side. With me? Yeah? So really, what we have and what we want to write down in our notes is 3 compared to 8 is the same as x compared to x plus 8. What can we always do in a proportion? We can cross multiply always, right? A fraction equal to a fraction, we're allowed to cross multiply. So if we do that here, now be careful, 3 has to multiply by x and 8. So we get 3x plus 8 equal to 8x, right? What, Micah? Yeah, didn't you just say what to do? -3x. Ooh, -3x on both sides. Group up those like terms. And we then get 5x is equal to 8. How do we solve for x? Divide by 5. X is 8/5. Or 1 3/5. Or 1.6. Sorry, my smartboard is possessed. Have a wonderful day. Homework is 9 and 4. Oh, rulers, stack them up on my round table, please. Stack your rulers on my round table, please.